Okay, we are continuing with our transformations unit and we are moving on to stretches. In the workbook, this would correspond to lessons 5 and 6, though for the lessons on stretches, I'm just going to be using my own note package. And again, I've handed it out blank copies on the Google Classroom. So before we actually get into stretches, I want to do a quick review that you could just jot down at the top of the page on what we've done so far for transformations. So the first two lessons in the workbook covered a concept called translations. So essentially what a translation is, it's taking your graph and translating it, which is moving it either left, right, up, or down. It does not change the shape of the graph. So a translation, we had two parameters. They were the k parameter and the h parameter. And what happens is you're given an original function, y is equal to f of x, and after it undergoes the translations, the new function would be y minus k is equal to f of x minus h. And then you just need to be able to look at this and say to yourself, okay, this k value, which I could also write on the right-hand side of the equation by adding k to both sides, the k value was your up and down move, and that was called your vertical translation. And your h value moved your graph left or right, and that was called your horizontal translation. Then there was two videos or two podcasts on reflections. So after translations, we did reflections. And a reflection, we reflected it either in the x-axis or in the y-axis. And what our equation looked like, so we had our original function, which is y is equal to f of x. And after it underwent these reflections, it would be y is equal to negative f in bracket negative x. So if you see the x, or sorry, the negative outside of the function, that was your vertical reflection. And if you see the negative within the function, that was your horizontal reflection. Oops, horizontal reflection. Okay, what we're going to do now is we're going to take a graph and we're going to stretch it. So I'm going to introduce two new parameters for stretching, and those two parameters are the A value, which you did in Math 20-1, and then the B value, or the B parameter. So what it's going to look like is we're going to be given our original function, y is equal to f of x, and after it undergoes those two stretches or those two transformations, our new function would be y is equal to a f open bracket b of x. So again, the a value is outside of our function, and that's always going to be a vertical. So that's going to be our vertical stretch. If it's within the function, your b value, that's going to be a horizontal stretch. So anything that applies to the x is always your horizontal, right? So the h parameter applied to the x, that's going to be horizontal. If it's outside of the function, it applies to your y value, and that's going to be vertical. Okay? So first thing here, it says a stretch, unlike a translation or reflection, changes the shape of the graph. A translation just translated the graph, it just moved the graph. Stretching, we're actually going to change the shape of the graph. So let's quickly look at something that we did in Math 20-1. So in Math 20-1, you were given quadratics, right? So you were given the graph of y is equal to x squared. Then what we did in 20-1 is I said, okay, well, what would happen? So there's an invisible 1 here. So the a value is 1, right? It's in front of my function. So the a value is 1. Then I said, okay, well, what would happen to your graph if you took out that a value and we put in a fraction? So let's say 1/3 x squared. So in 20-1, we would have taken out our calculators and we would have punched in x squared. You would have graphed this. Here's your parabola for y is equal to x squared. Then I would say, okay, now let's graph y is equal to 1/3 x squared. And let's see what the graph looks like if we're changing our a value from a 1 to a 1/3. As you could see, this fraction, which is 1/3, makes our graph wider, right? So when a is a fraction, it makes our graph wider. So if a is less than 1, greater than 0, it's going to be a wider graph. What's happening is the graph is actually compressed. Okay. If our a value, so this blue graph is our graph of y is equal to x squared. So our a value is 1 there. If I then say, okay, graph y is equal to 4x squared, so I give you an a value that is greater than 1, what happens is this blue graph is going to be stretched up to this graph here. And so when our a value is greater than 1, we are going to have a graph that appears more narrow. Okay, so again, that was just a review from 20-1. And again, what this first part, or what this, I guess, entire lesson will be on, is stretches. And we're taking our original function, and what we're going to examine now is the a value, which is outside of the function, and then a b value, which is inside of the function. If it's outside of the function, the a value is a vertical stretch, and our b value is going to be a horizontal stretch. Okay? So let's look at this first example. It gives us a graph, and we're going to look at what happens when we have a given graph. So y is equal to f of x. So this is our given graph, y is equal to f of x. And the only transformation we're going to look at now is we're going to add an a value to it. So y is equal to a f of x. And you know from the previous slide that the a value now is what we call a vertical stretch. So I'm just going to write vs above that. That's going to be a vertical stretch. Okay, so let's look at what happens. Now, the a value affects the y coordinate. Okay, so the vertical stretch affects the y coordinate. So what the mapping is for a vertical stretch is you have your original coordinate, and then your new coordinate is going to be the x value doesn't change, and it's going to be whatever your a value is times your y value. So your vertical stretch affects the y coordinate. So I'll show you what happens. Let's take this point here, which is -6, 4. So they've actually given you that point right here. So -6, 4. And actually I'll write here, so x comma y is going to go to x comma a y, and we know that our a value, they want our a value to be 2. Okay, so they want our a value to be 2. So then it's going to be 2 times whatever our y value is. Okay, so you take a point, and they gave us -6, 4, so it's just a nice point on my graph. And let's see what the new point becomes when it undergoes a vertical stretch and the a value is 2. So what happens is the x value stays the same, and our new y value is now 4 times 2, right? So 4 times 2 is 8. So it's whatever the y value is times 2. So this point here is now going to be at -6, 8. So this point stretched up, and that's my new point. Let's look at a second point, which is this guy down here, -2, 0. So what I need to do is my x value stays the same, so it stays at -2, and then it's my whatever my y value is times 2. So my y value is 0. 0 times 2 is 0. Let's star this. That point doesn't change. And remember from your last lesson what that's going to be called. That's going to be called an invariant point. Okay, let's look at 0, 2. So this point right here, 0, 2. When you apply the vertical stretch to this, your x coordinate stays the same, and your y coordinate, we multiply it by 2, right? So the y coordinate would be 0, comma 4. So this point here is going to get stretched up now to here. Okay, let's go to 2, comma 0. 2, comma 0, that's going to be an invariant point because if you multiply 0 by 2, it doesn't change. Okay, so that new point stays here. And then our last point was 6, 6, comma 4. So that was this guy right here is at 6, comma 4. So when we take that point and we multiply the y value by 2, our new coordinate is going to be 6, comma 8. Which is right here. So that point got stretched up. Now, if we take a ruler and we connect all these points, and I'll do this in blue, here's what our new transformed graph looks like. Okay, so that would be our new graph. I'll erase this and this. This is our new graph after it's undergone a vertical stretch. Now, one thing I need to write down that we need to know. So our original function was y is equal to f of x, and that was transformed to y is equal to a f of x, and our a value was 2. So I'm going to actually erase the a and I'm going to put in a 2. So our a value is 2. Okay, so what I always tell students to write is write what parameter that is. So that's our a parameter. Our a is equal to 2. Then always say, well, what was the transformation? So we always say vertical stretch. And then what we need to do is for vertical stretches and horizontal stretches, we need to say what the stretch factor is. So the stretch factor of this graph, it was a stretch factor of, for your a value, it's nice and simple. It's whatever your a value is. So it was a stretch factor of 2. And if you look at that, that makes sense, right? This 4, I stretched it by 2. I multiplied it by 2, right? 4 went to 8. 2 went to 4. 4 went to 8. So it's a vertical stretch. A value is 2, vertical stretch, stretch factor of 2. So for example, before we do these other questions, like let's say I gave you this, y is equal to 5 f of x. You would say, okay, that's an a value. A is equal to 5. It's a vertical stretch. The stretch factor is equal to 5, right? What would happen here? My coordinates for mapping would be x comma 5y. So each point, I'd multiply the a value times 5, right? If my a is 5. So with a value, b value is going to be a little bit more tricky, but for a value, super straightforward. That's my a value, that's my vertical stretch, and that's also my stretch factor of 5. Okay. Okay, so let's fill this in. So it says when a is equal to 2, right? So our a value is 2. It results in a vertical stretch by a factor of 2, and the mapping is x comma y. The new coordinate is x comma a times y, so x comma 2 times y. The invariant points on your graph are the points that do not change. So the invariant points were negative 2 comma 0. So remember this guy was an invariant point and this guy was an invariant point. And 2 comma 0. So negative 2 comma 0 and 2 comma 0. Okay. The domain of my new graph. So if you look, so remember domain is your x values, right? Did my domain change at all under a vertical stretch? So what do you guys think? Did the domain change in either of my graphs when we undergo a vertical stretch? And the answer is no, right? The vertical stretch does not affect the x values, it affects the y. So my domain does not change under a vertical stretch. So my domain is negative 6 to 6. That's my domain. And we could say domain does not change. Triangle for change in a vertical stretch. Okay. What's affected by a vertical stretch is the range. That's what a vertical stretch changes, is the range. So my original range was 4 to 0 or 0 to 4, but my new range, so actually let's write our original range. So the original range was smallest y value is 0 and the biggest y value is 4. Okay. And my new y values, the biggest y value is 8, the smallest y value is 0. So my new range is 0, 8. And that makes sense, right? Because the vertical stretch, the a value affects the y coordinates. So 0 times 2 stays at 0, but 4 times 2 changes to 8. Okay. Make one more note on this page. Vertical stretch does not affect x-intercepts. Those would be our invariant points. So if a graph undergoes a vertical stretch, the x-intercepts remain invariant. Okay, what we're going to do now is we're going to take this exact same graph, but here's what our a value is. So our a value is now 1/2. So a few things, always write that down. Write down your parameter. That's your a value. A is equal to 1/2. Then always write down for me that that is a vertical stretch by a stretch factor of whatever that a value is, 1/2. The mapping is going to be x comma y to x comma a times y. So x comma y to x 1/2 times y. So for this example now, they want our a value to be 1/2. So all of our y coordinates are going to be multiplied by a half. Okay? So we're taking the exact same points. So -6, comma 4 is right here. And now what we're going to do, so I'll write it over here, -6, comma 4. That new point, -6 stays the same, and y gets multiplied by a half. So 4 times a half is 2. My new point is -6, 2. So this is going down, so it's a compression. We still say it's a vertical stretch by a factor of 1/2, but the graph is actually going to be compressed. I'm going to be pushing this graph down. Okay, next point, -2, 0. So -2, 0. X value stays the same, y value multiplied by a half. -2 times 0, or sorry, 0 times a half is 0. So that point doesn't change. Okay, 0, 2. Multiply that y value by a half, and we're going to go to 0, 1. So 0, 1. So again, this point here got pushed down. This, I hope you see, is going to remain invariant. So 2, 0 is going to stay at 2, 0. And then this point, what is that? 6, 4. X value stays the same. Y coordinate gets multiplied by a half. So that's going to go to 6, 2. So that point went down. Okay, let's take a ruler and it's the exact same shape of the graph, and I've stretched, I've compressed the points. Okay, so this would be our new graph. 6 comma 4 goes to 6 comma 2. Okay, so with an A value of 1/2, it still results in a vertical stretch. And the stretch factor of 1/2. So whatever the A value is, that's your stretch factor. The mapping, it's always x comma y to x A times y when we have a vertical stretch. So it would be x comma y to x comma 1/2 y. Okay, the invariant points, this is the same as the last example. So your invariant points are your x-intercepts, which are -2 and 0, and 2 and 0. So those are your invariant points. The domain, again, the domain of this graph did not change. So it went from -6 to 6. The range of this graph did change. Okay, so the range of this graph, let's do the range of the original graph again. So the original graph was 0, the smallest y value is 0, the biggest y value was 4. And our new range, the smallest y value is 0, the biggest y value is 2. So vertical stretch affects the y values, it affects the range on your graph. So again, vertical stretch affects range. And what's happening to these y coordinates is they're being multiplied by that a value. So 0 times 1/2 is just 0, but 4 times 1/2 is 2. Okay? Okay, so we are done the a value. Let's look at the b value now. And the b value, it's going to be slightly more complicated, just because there's one additional sort of thing you have to consider for the b value. So let's just write what our transformation was again. So y is equal to f of x, and we're undergoing stretches. So we either have an a parameter or a b parameter, or we could have both. Y is equal to f b of x. If it's outside of the function, what we just did on the previous two examples, that's a vertical stretch. If it's inside the function, it's a horizontal stretch. Okay, so we're going to be looking at this b value, which is a horizontal stretch. So what we're going to do, so it's the, again, exact same graph, but we're now dealing with the b value. Okay, so here's what we're graphing. Okay, and so we had our original function, y is equal to f of x, and this is going to go to y is equal to f2 of x. So you know that this is your b value, so you're going to always say b value is equal to 2. And then we're going to write stretch factor is equal to, and I'm actually going to leave this blank. We're going to look at the graph first before we figure out the stretch factor, because for the b value, it is not going to be 2. So I'll show you what the b value will be. Some of you will be able to figure out it once we get graphing it. Here's what the mapping is. X comma y is going to be mapped to x over b y. So remember that the horizontal stretch, so, oh, and we should write that this is a horizontal stretch. It affects the x coordinates because it's next to the x. So the b value affects the x coordinates, and it's going to be x over whatever your b value is. So again, it's going to be x comma y, x over 2, because that's my b value, times y. So I've got the points here for you. And actually, instead of just filling out this chart, like these are the coordinates, right? I want to rewrite all of these 1, 2, 3, 4, these 5 coordinates. So let's rewrite these 5 coordinates so that we could do our proper mapping. Okay, so the first point was this guy, which was -4 comma 4. -4 comma 4. So that point, when you divide, so the y value stays the same, and you take your x value and you divide it by 2. So that's going to be negative 2. Okay, so my new point is going to be at negative 2 comma 4. So this point, watch what way this point goes. The y value stays the same. This point is going to undergo a horizontal stretch, right? So horizontal, you guys, is like left, right. So this point is going to be stretched in. Now, let's look at this next point, negative 2 comma 0. Okay, negative 2 comma 0. Let's see what happens to this point. So when you take your x value, which is negative 2, and when you divide it by 2, we're going to get negative 1 comma 0. So let's put that point in. So this point is now here. It moved over. Okay, this third point was x is 0, y is 2. When we divide the x coordinate by 2, we're going to stay at 0, comma 2. So that's going to be our invariant point. So that guy stays. This point here is 2 comma 0. So let's write that point. And again, what we need to do to the x value is we need to divide it by 2, right? So that guy divided by 2, the new point is going to be 1 comma 0. So it's going to be there. And then, and you know what, I should have, just so we're keeping our points. Okay, so let's take this last point. So that last point, x is 4, y is 4. So what happens to that point? That x value gets divided by 2. So that's going to be 2 comma 4. So our new point, 2 comma 4, is up here. So again, that point, oh, sorry, 2 comma 4 is right here. Okay, let's take a ruler and let's connect those dots. So this point to here, that's my invariant point, down and up. If I erase everything, this was my original function, and then this is my new function where the b value is 2. Okay, let's see if we could figure out what the stretch factor is. So what's happening? Look at your x coordinate. I'm going from 4 to 2. I'm going from 2 to 1. If I had an x coordinate of 8, so let's say I had an x coordinate of 8, my new x coordinate would be 4. So what do you think the b value or the stretch factor is if I'm going from 8 to 4? What does everybody think? The stretch factor is 1/2. Okay, so the stretch factor is 1/2. And what's really interesting about the b value is it's always going to, or the stretch factor, it's always going to be the reciprocal of whatever the b value is. So for example, if I gave you this function, y is equal to f(3) of x, you would say, okay, that is my b value. B is equal to 3. This is a horizontal stretch. The stretch factor is going to be the reciprocal of 3 over 1, which is 1/3. So it's xy would be mapped to x over b times y. That would be your mapping. So the b value, the b value tells you that it's a horizontal stretch, but the stretch factor is always the reciprocal. Okay? Okay, so again, the b value of 2 results in a horizontal stretch factor of 1/2, right? And x comma y is going to be mapped to x, so it's x comma y is going to be mapped to x over b times y, which is x over 2 times y. Invariant points, the invariant point on here, the point that did not change, was the y-intercept. So the y-intercept was 0, 2. So star that and write down y-intercept. If it undergoes a horizontal stretch, the y-intercept is going to be invariant. Okay, so because we're now dealing with the x-coordinates, what changes between domain and range? What do you guys think? So look at your graph. The mapping affects the x, which means the domain is changed, right? So the domain is what's affected when you undergo a horizontal stretch. This new domain is from -2 to 2. The range remains, it's not affected, right? So a horizontal stretch does not affect the y values. So the range of my new graph, the biggest y value is 4 and the smallest is 0. Okay, let's look at this. We're going to be exploring the b value again. Okay, so it looks a little bit complicated because there's several graphs in one. For this example, what I want you to see is that this is a radical graph, and it's the square root of x. So y is equal to this square root of x. So if I was just to graph that really quickly, y is equal to this square root of x. That's what the graph looks like. So this blue graph is my original graph, okay? And what we're going to look at is, let's say we take this original blue graph and I put a 4 in front of the x. So y is equal to, so we're going to look at this one right here, the square root of 4x. Okay, so hopefully what you see is that this would be a b value, right? Because it's within the function. The a value would be if I put a 4 outside of the function, but this is within the function. So what you would do is you would say, okay, that's a b value. B value is equal to 4, and that is a horizontal stretch. And the stretch factor is equal to, it's always going to be the reciprocal. So the reciprocal is 1 over 4. So what it wants you to do is it wants you to take this point on the original graph. So that point is at 4, 2, right? So take the point 4, 2, and what's the new point after it undergoes a horizontal stretch by a stretch factor of 1/4? So we know that it's x comma y to x comma, sorry, let me just erase this, x over b times y. Now, if our b value is 4, right? So our new point is going to be x comma y to x over 4 times y. So our new point on the graph is going to be, take that x coordinate, which is 4, and they want us to divide it by 4. So our new point is 1, 2. And here would be the point 1, 2. So if my b value is 4, my new graph is now this guy here, right? When my b value is 4. Let's look at what happens. Oh, and if you want to write this, so what's happening here, our x value is going from 4 to 1. We're multiplying our x values essentially by the stretch factor, which is 1/4, right? You're multiplying by your x value by the stretch factor. Okay, take your original graph, and now we're going to say what happens when our b value is 2. So b value is equal to 2. What's the stretch factor? Stretch factor is always the reciprocal of the b value. So stretch factor is 1/2. So you take your original point, and the original point was that guy there, which is 4, 2. And now what we're going to do is you're going to multiply your x value by that stretch factor of 1/2, right? So to get your new coordinate, you're going to multiply the x value by a stretch factor of 1/2. So 4 times 1/2 is 2, 2. And again, basically what we did was we took that x value and we divided it by our b value. So dividing it by the b value is the same thing as multiplying it by the stretch factor, right? 4 divided by 2 is 2, or 4 times 1/2 is 2. And that would be this graph here, right? Our new point is at 2, 2, which is right there. Okay, we haven't done any examples where our b value is a fraction. So if our b value is 1/2, what is our stretch factor? Our stretch factor is the reciprocal of 1/2, which is 2. So if our original point was 4, 2, what we're doing is it's x over b. And what's x divided by 1/2, right? So what's 4 divided by 1/2? 4 divided by 1/2 is the same thing as 4 times the reciprocal of this, 2 over 1, which is 8. So when you divide this by your b value, you could do that. You could say, okay, I want to do 4 divided by my b value, so 4 divided by 1/2. Or you could just say, I'm going to take that 4 and I'm going to multiply it by the stretch factor. So 4 times the stretch factor is 8. And our y value stays the same. So that graph, 8, 2, is right here. So that would be this guy here. Our last one, what's your b value here? B value is equal to 1/4. What's your stretch factor? Stretch factor is the reciprocal. So the reciprocal of 1/4 is 4. So if I take my original point, what was my original point? The original point was that guy there, which is 4, 2. Take that original point, and what you do is it's x over b, so it's 4 divided by 1/4, or you could say 4 times the stretch factor. So our new point would be 16, 2, because you're going to multiply it by a stretch factor of 4, right? So the new point would be this guy here, and that would be the graph. So again, all I've done is I've taken the original graph of y is equal to the square root of x, and I put in different b values, right? The stretch factor is always the reciprocal, and you could multiply your x value by the stretch factor, or you could divide your x value by your b value. So examining the trend, the x values are multiplied by a scale factor of 1 over b. Okay? So you're just multiplying your x values by the reciprocal of the b. No, sorry, you're multiplying your x value by the stretch factor. And we'll look at an example here. Okay, so let's do this guy, and then we'll summarize everything. Okay, so for this one here, here's our transformation. So let me just move this down. Okay, so let's see what we're doing in this question. So again, exact same graph. We're just going to look at y is equal to f of x is what they've given me. And now they're saying, please transform this to y is equal to f of 1/2 of x. Okay, that is a b value because it is next to our x. So our b value is equal to 1/2. This is a horizontal stretch. The stretch factor is always the reciprocal of your b value. So the stretch factor is 2. When we map this, it's x comma y to x over b times, or sorry, x, let me just get rid of that. Okay, so when we're mapping, it's x over b times y. Now, because my b value is a 1/2, we're saying x divided by 1/2, right? So some students, that's confusing, x divided by 1/2. Well, that's the same thing as xy to xy. So something divided by 1/2 is the same thing as multiplying it by 2. You're multiplying it by the stretch factor. Okay, so we always multiply by the stretch factor. Okay, let's get our points and then let's undergo our transformation. So again, our original is x comma y and our transform function is 2x. It's whatever you multiply by the stretch factor. Stretch factor is 2. So 2x times y. Here's our points here. So -4, 4. When you multiply that 2 by 2 goes to -8, 4. So my first point is -8, 4, 5, 6, 7, 8. So it's going to be out here. The second point on our diagram is -2, 0. Multiply that x coordinate, the x coordinate of -2, multiply it by 2, and we get -4, 0. Right? So this point horizontally stretched out there. Let's take this point here, which is 0, 2. And let's multiply our x coordinate by 2, and it's not going to change. So 0, 2. So invariant point, horizontal stretch does not affect your y-intercept. So my new point is there. 2, 0 will be next. So let's map 2, 0. Multiply that x coordinate by 2 and we get 4, 0. So my new point is going to be here. So that one underwent horizontal stretch by a stretch factor of 2. And the last point was at 4, 4. So that was our last point. So 4, 4. Multiply that x value by 2, and we're going to get 8, 4, which is going to be slightly off our graph. 6, 7, 8, which will be about there. And then get your ruler. And create your new function, which is, they're calling it g of x. So this blue graph that I just drew, that's the transformed function of f of x. When the b value is 2, it's undergoing a horizontal stretch, and the stretch factor is 2. So when the b value is a fraction, it results in a horizontal stretch by a factor of the reciprocal of the b value, which is 2. And when mapping, it's x comma y to x times the stretch factor. So the stretch factor is 2. The invariant points, remember, are the y-intercept. So the points that don't change are going to be invariant. So that guy there, which is 0, 2, is your invariant point. This, remember your b value, it affects your x's, so your domain is affected. Your new domain now is -8 to 8, and your range is unaffected, 0, 4. So remember that when it undergoes a horizontal stretch, the range doesn't change. Okay, let's look at a summary now. So for our summary, what I just want you to write, maybe we'll write it at the bottom. So y is equal to f of x is our original. And after it undergoes a transformations, it's y is equal to a, f, b of x. Your a value is a vertical stretch. Your b value is a horizontal stretch. Okay, so the a value here is a vertical stretch. The a value is in front of the function. Remember that the mapping for this, it's x comma y to x comma a times y. So again, if I gave you, let's say y is equal to 3 times f of x, that's a vertical stretch. A value is equal to 3. Stretch factor is equal to 3. So you always multiply your coordinate by its stretch factor. Now, what this is saying, this point here, it's saying, well, what happens if we did this? Y is equal to -3 f of x. So a vertical stretch about the x-axis by a factor of the absolute value of a. So I'll explain what that means. If a is less than 0, then the graph is also reflected. Because remember, if we have a negative in front of our function, that's going to be a vertical reflection. So if I give you a negative, two things are happening here. If I say, what is the a value? The a value is -3 now, right? So the a value is -3. That is going to be a vertical stretch by a stretch factor of the absolute value of a. So when we do stretch factor, you guys, this is super important. You never say that your stretch factor is negative. So you just say that this is, the a value is -3, but it's a vertical stretch by a stretch factor of 3. And what this negative tells us, so and a reflection, right? And a vertical reflection is what this tells us. So a vertical reflection in the x-axis. Okay. What this mapping would be x comma y to x comma, remember y changes to -y. So we do take that a value and we just put it in front of the y. So -3y is what our new mapping would be. But again, that tells you that the negative tells you that there's a reflection. The a value is -3, but the stretch factor, for stretch factor, we never say negative. We just say the stretch factor is 3. Okay? Now, for the b value, it's within the function. That's a horizontal stretch. Okay? The stretch factor, so if I gave you y is equal to f2 of x, the b value is equal to 2. The stretch factor is always the reciprocal, so 1 over 2. The mapping is x comma y to x over b times y, so it affects the x coordinate. Or basically what you do is you multiply the x coordinate by whatever the stretch factor is, right? So x over b, which is 2, or 1/2 times your x value. If b was negative, so again, let's do an example where b is negative. So y is equal to f negative 1/4 x. Okay, so what you're going to do if you see this, you're going to say that that is my b value. B value is -1/4, right? So the b values and the a value, they could be negative. B value is -1/4. Then you say that's a horizontal stretch. You tell me what the stretch factor is. Stretch factor is always the reciprocal of the b value. And we never say negative stretch factor. So the stretch factor is 4. right? The stretch factor is 4. What that negative does, though, is remember that x changes to negative x. So that tells you that there's a horizontal reflection about the y-axis. So it's a horizontal reflection in the y-axis. Okay, and if we were to do the mapping for this, the mapping would be x comma y to, it's always x over b times y. So x comma y. Now, because it's a fraction, right? I don't want to go x divided by negative a quarter, just multiply it by the stretch factor. So the stretch factor is 4x, but we got to put the negative. So when we're doing our mapping, we always include the negative, right? Because that's going to tell us that's the reflection. But when I give the stretch factor, I just say the stretch factor is the absolute value of the reciprocal of the b value. Okay, so again, to summarize, it's x over b, a times y, or x times the stretch factor, y times the stretch factor. So a long lesson, but that's part 1 of 2 for this lesson.